stage is ready. Let's introduce our next keynote speaker. This time, the theme's gonna be around quantifying grid intelligence, the role of measurement chains in smart grid realization. Joining us on stage is Carina Lehmal, CTO at Greenwood-power. Welcome. The stage is yours.
Great. So my name is Carina Lehmal, and I'm the CTO of Greenwood-power, and it's my pleasure to be here today and talk about the pivotal role that measurement chains play in the realization of a smart grid. Okay, so to set the stage first, let me give you the fundamentals, what the smart grid really is. So we probably know that, but let's recap that for a minute. A smart grid is really the representation of the future generation of the power system. And how is it doing that? By integrating advanced technologies that enhance the efficiency, the reliability, and the sustainability of the whole power delivery. And unlike in the traditional grid, a smart grid uses digital communication and control systems to make a real-time connection that can then be used to mitigate a blackout, to forecast something when it is done right. So traditionally, the grid looked like that. On one hand side, we had the generation. This was predominantly a big or many large power plants that had a voltage and a frequency control. And then the whole generation went from top to bottom to the consumer side in a unidirectional power flow. But now this is really changing. With the integration of wind and PV, we have suddenly in the distribution grid on the medium voltage level and on the low voltage level and a generation. So that means our consumer is not a consumer anymore. How does it work? Yeah, so the consumer is not a consumer anymore, but it's a prosumer, so they produce as well as consume energy. And that means the whole distribution grid, which is here with substations in the medium voltage level, is a black box for the utilities. And the utilities now have to integrate a measurement infrastructure, they have to integrate a relaying infrastructure. And this means they have to make a whole complete measurement chain that consists of different components. And what does it also mean? That the power flow does not go from the generation side on the high voltage level to the low voltage level, but also from the low voltage level up to the distribution, to the medium voltage level, and to the high voltage level. And the utilities have to combat this, they have to control it. And now that we have the fundamentals solidified, let's look at the measurement chain itself. So because if we understand what the measurement chain consists of, we can think about where should funds go, what kind of policies do we need, and what kind of product development is needed for the power grid to become the smart grid that we want to have. So at the first point, we need some kind of initial link that is collecting and sensing the signals that we want. For utilities, the main focus here is on voltage and on current, obviously. And from this, we can get a frequency and regulate that. Then, when we have those signals, this goes further to the data acquisition, where different algorithms can be applied. For example, we would filter the signal, and then we would get all the relevant data from the signal. But now what are we doing? Those data is now collected and then goes further to the SCADA system the utility utilizes or to a cloud-based solution. It's really not one solution. Every utility has several solutions, and the initial link in this whole measurement chain has to adapt to everything. So we cannot make only one sensor, because this is what the initial link is called. but we have to think about what the sensor should be able to do. And this is now the big question. What should the sensor actually be able to do? To be able to be multi-compatible. It should be able to be small, because obviously we have existing infrastructure, and we don't want to invest additional funds to that. And it should have a high quality, because as we heard before in the panel discussion, when we have crap in an AI system, we also get crap out of it. And if we don't have a high-quality sensor that measures correctly, and then the data acquisition can go from there and filter out the relevant data, then we also get the right results. If we don't do it, we get the wrong results. So it makes sense to make a little bit of a deep dive into sensor technology. So let's think about the infrastructure. Of course, we have the high voltage, we have the big transmission lines, we all know that, and then we have many substations. And now let's take Europe, for example. Estimated, there are around 3 million substations in Europe. Could be a bit more, could be a bit less, depending which countries you count in the end. But now to digitalize one substation, you need around 15 sensors. And now let's multiply those numbers, and we get around or more than 44 million sensors if we really want to digitalize 100% of all the substations only in Europe. Now we have the US, now we have Asia, we have India, we have Australia. You see that the number of sensors goes up and up and up. And of course, there are now studies that tell us, okay, how many substations should be digitalized? And one of those numbers is around 25%. But still, let's take the number 44, take 25% of it. We still have over 10 million of sensors that should be produced, that should be developed, and it should be integrated. So this is not only an issue of where is the fund coming, but how can we produce that? Who is going to produce it? Where do we get the resources from? And who is deploying that in the grid? So we have kind of a prerequisite of what the sensors should be able to do. They should have a compact size, because a substation has only so much space, and we don't want to rebuild them, because this is a lot of money. Then it should be a quick installation, because again, a long time is a lot of money. And it should be a plug-and-play solution, because otherwise you have to adjust stuff in the field. And again, this needs time, this needs money. And yes, the last point is money. It should be cost-effective, because otherwise a smart grid is not feasible in the end. And now we have talked about high-quality measurements. So we don't only have this prerequisite of, let's say, wish list, but we also have technical specifications that we have to add to that wish list. Because we need to have a certain accuracy class if the utility wants to meter something, if they want to bill a customer with something. And we need to have a certain protection class to protect a transformer from overloading. So it is important that the sensor has the right accuracy class, the right protection class, and of course, with type test, keeps those values. But there is also the thing of external influences. We all know it, there is an electrical field, there's a magnetical field, and both of those fields have an influence on the sensor. So the sensor has to be resistant to neighboring fields, because we have 3-phase systems, and those phases are very close together. And if now I have one sensor on phase A and another on B, and those two sensors are influencing each other, well, as the gentleman before said, we measure crap. So we have the neighboring field interference sensor has to be resistant against. We have the precision inaccuracy, because every installation is slightly different. And we have harmonics that we have with all the PV, with all the wind integration, with the inverters. Because inverters have electronic components, and those make harmonics, due to the pulse bridge rectifiers. And this is quite a wish list, I guess. But only if the sensor fulfills this wish list, we can do, for example, predictive maintenance. And this is important for every utility, because without predictive maintenance, how should we know if there could be an outage, or how can we forecast it? this is predictive maintenance, and we have to have high quality. And the same thing for fault detection. We need to be able to tell where the fault is happening. And the same thing for grid optimization. And this is super important. We want to integrate renewables, but this we cannot do without controlling the whole thing because they are weather dependent. So only with those things, with the whole wish list, we can fulfill a smart grid. So now, of course, there are some challenges like data security, interoperability, and scalability, as well as workforce skills. I talked about them very shortly, but by really thinking about the whole measurement chain, we can deploy them and we can take from these challenges an opportunity for innovative technologies. And this is now where Greenwood-power comes in. We produce non-conventional sensors for voltage, for current, and we basically fulfill all the requirements that are needed to get the wish list done and make a smart grid. And we have a very diverse product range, from air-insulated switchgear to gas-insulated switchgear to outdoor applications. So to summarize the whole thing, we want to make the vision of a smart grid a reality, and now we know what we need for that. We need, as a first puzzle piece, a sensor, then a data acquisition system, and then the SCADA or cloud-based solution of the utility. And this means for the utility, CapEx costs. Many, many high CapEx costs. So we know now where the funds should go, to CapEx costs for utilities and to research for sensors. And with that, I thank you very much for your attention and look forward to any pending questions. You have my contact information on the slide, or you can talk to me or reach out on LinkedIn. Thank you.